throughout the math team season, we run into a few concepts that we don't usually use in our high school math classes. One of those is going to be Ceva's theorem. Ceva's theorem says that in any triangle, if three Cevians meet at a single point, then the following relationship is going to be true. Now, first of all, what's a Cevian? A Cevian is going to be any line segment in a triangle that connects a vertex to its opposite side. So here we have three Cevians, one that goes from vertex to opposite side, vertex to opposite side, and vertex to opposite side. If we have this situation where all three of them meet at a single point, that's when this relationship is going to hold true. Now, you can look online and see this expressed in a lot of different ways. I like labeling the triangle in this way, that because we have three Cevians, it's going to divide each side of the triangle into two parts. I just start on one of these divided segments and work my way around the triangle going A, B, C, D, E, F. Then the relationship of A to B times C to D times E to F will always equal 1. So let's see Ceva's theorem in action here. Suppose AB, AC, and BC have side lengths of 13, 14, and 15 respectively. That would mean that if we call this vertex A and this one B, its side length will be 13. A to C is going to have a length of 14, and B to C will have a length of 15. Then it says if this ratio of AF to FB is 2 to 5, that means that there is some point on AB that we can call F. And it will divide that side by the ratio of 2 to 5. Now, obviously, it can't be 2 and 5 because that would add up to be 7. So there's got to be some sort of, constant of proportionality in there. So we'll call that 2x and 5x. Similarly, we have the ratio of CE to EA is 5 to 8. So that means that there is some point on AC, maybe right here, call that point E, such that CE to EA is 5 to 8. So CE would be the 5, E to A would be the 8. Obviously, 8 plus 5 is 13, not 14. So again, we have a different constant of proportionality. Now, what my plan is to use Ceva's theorem by drawing in my Cevians. Right. The third Cevian would have to go from vertex A through this point to meet B on the other side. Then we can use Ceva's theorem because all of these Cevians have to meet at a single point. In doing so, that divides up side BC. So I'll just call these sub-segments here M and N. Now, when you're setting up Ceva's theorem, it's important to start at one of these little sub-segments and set up your fractions, working your way around the triangle. So if I start with that 8y, then we'll go to 5y times n over m times 5x over 2x. And the product of all of them will equal 1. Now we can go ahead and just see how this thing plays out. For instance, I got y over y, so those will cancel. X over x, those will cancel. This 5 and this 5 will cancel. Then I'll be left with 8n over 2m is equal to 1. Multiplying both sides by the 2m, 8n is equal to 2m, or 4n is equal to m. That's super helpful because I just said that m is equal to 4n. So if I go back to my diagram, this side m is equal to 4n. If I added together that 4n plus the other n, then that's got to equal 15. 5n is 15, and n must be 3. Now, 3 is not our answer. Go back and answer the question. The question asks us to find B, D, and DC. So, BD. That must mean that this point here is our D. BD is 4 times n, which was 3. So BD is 12. And DC, that is n, which is 3. And there are our two answers.